This segment we're going to talk about gas-vapor mixtures or psychrometrics. So we've looked at ideal gas mixtures so far, but we haven't really looked at the case where one of those components goes through a phase change. And that could be the case if you're talking about an HVAC application or air conditioning application where you've got condensation or evaporation of water vapor in atmospheric air. Atmospheric air is composed of dry air and water vapor. So by Dalton's law says that the overall pressure is equal to the sum of the component pressure. So I've got two components. I've got dry air and I've got water vapor. So I'm going to use a little subscript A for the dry air, a V for the water vapor, just because it's annoying to write H2O every single time. So we've got these ideal gas relationships. Can we still use them for this mixture? Well, for dry air, yeah, probably. That's not too much of a stretch. We always treat air as an ideal gas. But what about the water vapor? That's always a question mark. Well, let's see if we could do that in this case. So if we look at a TV diagram, I draw a little line of constant pressure, and I think to myself, okay, well, I know that atmospheric pressure is about 1 bar. So let's see the temperature at which water would condense at 1 bar. And if I look at my table A3, I see that the temperature at which it condenses is the saturation temperature. So it's 99.63 degrees Celsius. So that tells me if I'm below 99.63 degrees Celsius, that puts me in the compressed liquid region, the liquid phase. If I'm above that, that puts me in the superheated region, in the gaseous phase. Well, I mean, that tells me that if I'm below 99.63 degrees Celsius, I shouldn't have any water existing as a gas in the atmospheric air. I should have no moisture in my air. That makes no sense. Room temperature is 25 degrees Celsius, and you know there's moisture in the air. So how is that possible? Well, the answer to that is that properties are evaluated at the partial pressure, not the overall pressure. So I know that the partial pressure is equal to the mole fraction of the vapor times the overall pressure. And if the overall pressure is about 1 bar, well, let's see, a typical value for the mole fraction of the water vapor is about 1%, 0.01. And I mean, that's a pretty small value, and it doesn't get much bigger than that. In the tropics, you're looking at about 4%, so 0.04. So your partial pressure might be about 0.01 bar. So let's look at what the saturation temperature is there. So if I had to interpolate in table A2 to get to a pressure that low, but I'm looking at about 6.949 degrees Celsius. So that makes a little bit more sense. That puts us firmly in that superheated region if we're above 6.949 degrees Celsius. And in fact, at typical air conditioning temperature ranges and vapor pressures, the water vapor can be assumed to behave as an ideal gas, even if it exists as a saturated vapor in that atmospheric air. And you'll have very little error in making that assumption. And you can verify that. If you know the vapor pressure, you know the critical pressure, you can look that up. And so you can calculate what the reduced pressure is. And if you go back to Thermal 1, where we talked about the generalized compressibility chart, if you looked up the PR, if you looked at where the PR value falls on that, if your PR value is less than 0.01, you're pretty close to ideal gas behavior, and that's the case here. So, long story short, for all the applications in this class, you can assume that the air, the dry air, and the water vapor behave as an ideal gas. So, with that being said, let's get some vocabulary terms out of the way. So my specific humidity, it's equal to the mass of the water vapor over the mass of the air. Pretty simple. So I just got finished saying that I can treat both components as an ideal gas, and I know by Dalton's model, the temperature of the components and the volume of the components are equal to each other. And so if I cancel out some terms, I put the specific gas constants of the air, the dry air, and the water vapor in terms of R bar and their molar masses, and I plug in some numbers, and then I repeat the same equation for some reason, I get that the specific humidity is equal to 0.622 times the partial pressure of the vapor over the partial pressure of the air. And by Dalton's model, since I know the relationship between the overall pressure and the component pressures, the partial pressures, I can rewrite the partial pressure of the air in just terms of P and P sub V. All right, so now let's look at the relative humidity. So this is the units you see here are kilomoles of water vapor over kilomoles of water vapor. So you'll get a decimal, or you can express it as a percent. But it's defined as the mole fraction of the water vapor in your atmospheric air at some given temperature and pressure over the mole fraction of the water vapor in the air if the air was fully saturated. In other words, if the water vapor was about to condense. So let's put this in terms of partial pressures and the overall pressure. Well, I see the pressures. I've got PV over P, and then I've got PV sat over P. And those denominators cancel out. So these are the terms I'm left with. And I'm going to rename that denominator, that PV sat, I'm going to rename that as P sub G. So what is P sub G? Well, let's look at a TV diagram. Here's my line of constant pressure that corresponds to the vapor pressure at some given temperature. And that little dot over there to the right, that represents the state of the water vapor as it exists at some temperature and pressure. Now, if the water vapor, or if the atmospheric air was fully saturated, in other words, the water was about to condense out, it would exist as a saturated vapor at that particular temperature. And so the partial pressure of the water vapor at that state is P sub G at that T. So P sub G, you can see, is the saturation pressure at that particular temperature. So I've got a relationship now, or I've got a definition for P sub G. And if the P sub V and P sub G are equal, if those two pressures are equal, then number one, your relative humidity is 100%, and it also tells you that condensation is about to occur. Okay, so it's a lot of information, but we're going to keep on plugging along. So going back to the specific humidity relationships, because I know that the relative humidity is equal to P sub V over P sub G, I can rewrite that last equation for the specific humidity. I can replace the P sub V's with relative humidity times P sub G. But all of these equations are on your equation sheet. You just need to be comfortable with them. All right, last topic is the dew point temperature. So this is the minimum temperature of the moist air at a given vapor pressure before that water vapor condenses. So once again with the TV diagram, here's my line of constant pressure or constant vapor pressure. I'm way out there. I'm out there in the gaseous region. That's the state of my water vapor as it exists in atmospheric air at some temperature and pressure. And if I condensed, or if the temperature decreased along that line of constant vapor pressure, where it hits the saturated vapor line, that's where the atmospheric air is fully saturated. That's where the water is about to condense out. So that temperature right there is the dew point temperature, and it's equal to the saturation temperature at that vapor pressure. So, all right. Well, I hope this was useful. I know it's a lot of information. Keep in mind that all of these equations are on your equation sheet. You just need to be familiar with them. Thank you for watching.